Welcome, everyone. Thank you so much for joining us this afternoon. My name is Erin Jench. I'm the Program Manager for Alumni Events at the College of Engineering and Applied Science. I'm excited to be here today with Professor of Electrical, Computer, and Energy Engineering, Lucy Pao, for this next webinar in our Alumni Webinar Series. As part of this series, we aim to showcase some of the amazing research that is happening at the college and bring our faculty directly to you for an exclusive look into their groundbreaking work. Now it's my pleasure to introduce Dr. Lucy Pao. Dr. Pao is a Palmer Endowed Chair Professor in the Electrical, Computer, and Energy Engineering Department and a Professor by courtesy in the Aerospace Engineering Sciences Department at the University of Colorado Boulder. Her research is primarily focused on engineering control systems, with applications ranging from atomic force microscopes to multi-megawatt wind energy systems. She enjoys working with her research students and still keeps in touch with many of her research students who graduated more than 25 years ago. Professor Pao, thank you so much for taking the time to share your work with us, with our alumni and friends today. I will go.
Thanks so much, Erin. Greetings, everyone. I appreciate being invited to give a webinar to alumni and friends of the college. Thank you for joining today. As Erin mentioned, I'll be talking about wind energy systems, which has been a focus of my research over the last 2 decades now. So I'm going to start by giving an overview of where wind energy is now. And then I'll talk about a couple of wind energy areas that are actively being investigated and pursued. And I'll talk a little bit about very lightweight downwind turbines, including tube-bladed concepts. And I'll also talk about floating wind turbines, such as this one. Now, before I actually get started on talking about where we are now with wind energy, let's first talk about how much power we use when we use various devices, just so everyone is calibrated on how much a watt or a megawatt is. So when you're actively using your cell phone, it's probably drawing about 1 watt from the battery. However, when you're charging your cell phone and it's plugged into the outlet, it's drawing about 10 watts from the wall power source in order to charge up quickly. Similarly, when you're using your laptop, it's probably drawing about 10 watts from the battery. And then when it's plugged in, it's probably drawing about 100 watts from the wall power source in order to charge up reasonably fast. Now, for TVs, it'll vary depending on the exact technology being used, LED, LCD, plasma, and whatnot. And of course, it also depends very much on the size of the display. But on average, TV uses about 100 watts. Now, there are many appliances in our house that use about 1,000 watts, which is 1 kilowatt. Now, on average, most households draw about 2 kilowatts of power. So you might have one of these appliances running, plus maybe a TV, and you might have your laptop, cell phone charging, and maybe you have some lights on. Now, if you're running several of these appliances at the same time, then of course you're drawing much more power. Now, more and more people are getting electric vehicles, and if you literally plug into a normal wall outlet at home, it will only draw about 1 kilowatt. Now, most people who buy electric vehicles will reconfigure one of their wall outlets at home to be able to charge their car more quickly, and these then allow the car to draw about 10 kilowatts. And there are, of course, supercharging stations then that allow you to charge even faster, and those allow the cars essentially to draw about 100 kilowatts. Now, 1 million watts is a megawatt, and that can power a very small town. And 1 billion watts is a gigawatt, and that can maybe power a city. Now, the amount of energy used is equal to the power multiplied by the amount of time that that power is needed. So if your dishwasher uses 1 kilowatt and it runs for an hour, it uses 1 kilowatt hour of energy. All right, so with that, let's now then take a look at the status of wind energy. So over the last decade, the installed wind power capacity worldwide has been growing at about 14% per year. There's now more than 730 gigawatts of installed wind power globally. Now, the country with the most installed wind power capacity is China. which has had an average annual growth rate of 27% over the last 10 years. The US is second with a growth rate of about 12% per year. And then Germany is third with a 9% annual growth rate. So together, China, US, and Germany have more than 60% of the world's installed wind power capacity. Now, this pie chart shows the top 10 countries in terms of installed wind power capacity. And of course, there are many other countries that also have installed wind power. Now, another way to compare countries is by what is known as wind energy penetration or wind penetration, which is the percentage of a country's electrical energy needs that is provided by wind. In this regard, Denmark is the #1 country. Almost half of Denmark's electrical energy needs is met with wind energy. And these are averages across a year. So Denmark actually does reach 100% instantaneous wind penetration levels at times, in which case they're trying to transmit excess power to other countries that can better use that power at those times. Now, the top 3 countries that I mentioned earlier in terms of installed wind power capacity, they actually have the reverse ordering in terms of wind penetration. So China has a very large population and hence large electrical demand. And so only 6% of their electrical energy needs are met by wind. In the US, we're unfortunately somewhat energy hogs, and only 8% of our electrical energy needs are being met by wind. And Germany is at about 27% wind penetration. Globally, less than 10% of the world's electrical energy needs are met by wind. So what all this data shows is that it is possible to achieve rather large wind penetrations and still have a stable power grid. And what this data also shows is there's still a lot of room for growth. And many countries are trying to increase their wind capacity in order to mitigate the effects of climate change. Now I'd like to talk about a couple wind energy research areas. Let me first talk about a very lightweight two-bladed downwind turbine concept that we've explored over the last few years. Before actually diving into that topic, let me first give a brief overview of some of the major components of land-based wind turbines. So this is a photograph of a 1.5 megawatt turbine at the US Department of Energy's National Renewable Energy Laboratory. This turbine is part of NREL's National Wind Technology Center that many of you probably know is only about 7 miles south of our campus. So this is a conventional 3-bladed upwind turbine. So the wind comes in from the left and these 3 blades come together at the hub. Now the rotor consists of the hub together with the blades. Now the nacelle houses the generator that sits and it sits atop the tower, and the foundation in land-based turbines usually consists of a lot of concrete that goes several meters deep into the ground. And these days it's tens of meters in diameter. All right, now wind turbines, as you've probably noticed, have become bigger and bigger over time. And this is because there are economies of scale that can lead to lower costs of wind energy as turbines get larger. Now, over the last 40 years, wind turbines have gone from hub heights of about 17 meters to now over 100 meters hub heights with at least 60-meter long blades. So in this range, we're at approximately 5 megawatt wind turbines. Now, we often see wind turbines really far off, and it's hard to appreciate just how large these machines are. If we compare with, say, a Boeing 747, so let's looking at this 100-meter hub height and about 120-meter rotor diameter. And if we compare this rotor area with, say, the Boeing 747 and a football field, including the end zones, hopefully you can appreciate just how large these structures are. Now, land-based turbines are not really getting much larger than 100-meter hub height and 120-meter rotor diameters. And this is largely because of road and railway constraints in transporting wind turbine towers and blades on land to their wind farm destinations. Offshore wind turbines, however, are not subject to the same constraints, and so they've continued to grow. And there are already a few commercial turbines operating that are more than 12 megawatt turbines and which have hub heights of 150 meters and have rotor diameters that are more than 200 meters. So these are blades that are more than 100 meters long. So these are, and some of these turbines now are being constructed in much larger wind farms that are expected to go into operation over the next couple of years. So just as a for instance, Vineyard Wind off the coast of Massachusetts, they are under construction right now, and they are building 13 megawatt turbines that are approximately of this size. Now, one of the reasons that the cost of wind energy decreases with larger turbines is that the power is proportional to the cube of the wind speed, and they're generally higher wind speeds higher off the ground. So building taller wind turbines allows them to capture much more power that's available at those higher wind speeds higher off the ground. So power is also proportional to the rotor area, and so of course taller towers allow you to put a larger rotor on them. So larger turbines also reduce the number of turbines required for a given site or a given size wind farm, and that cuts down on installation and operations and maintenance costs, and hence this trend towards larger and larger turbines. Now, along the lines of extreme scale turbines, I'd like to highlight a project that my research group has been involved in with a rather large team, and we've been working on this over the last 6 years. So we've been exploring a downwind 2-bladed as well as 3-bladed concept where we're really focused on really lightweight, flexible rotors. And we believe this downwind concept could be very beneficial as we get to very, very large turbines. So we call this downwind concept segmented ultralight morphing rotor, or SUMR. And I'll explain the terminology a little bit more in a bit. So we've been bio-inspired by palm trees, which hopefully you can see at the lower left there. Palm trees are about 20 meters tall, and so are pretty tiny compared to everything else shown here. The average size of onshore land-based wind turbines is now about 2.5 to 3 megawatts. And in this overall project, we've been designing 13 megawatt to 50 megawatt wind turbines. Our 13 megawatt wind turbine designs have blades that are over 100 meters long, and that's longer than a football field. And our 50 megawatt turbine designs have blades longer than 200 meters. And that, of course, means that the rotor diameter is more than 400 meters. So these are really large machines. And as I mentioned, there are some economies of scale with having larger turbines. If you have a 100 megawatt wind farm, it could consist of 40 2.5 megawatt turbines, or 8 13 megawatt turbines, or just 2 50 megawatt turbines. So needing to have the power cabling to only 2 turbines and needing to maintain and service only 2 larger turbines is easier than providing cabling and servicing for 40 2.5 megawatt turbines, or even 8 13 megawatt turbines. And so these are reasons that wind turbines have been getting larger and larger. The challenge, of course, is whether wind turbines can technologically be built reliably at ever larger scales. So why might downwind turbines with very lightweight blades be potentially better? Well, as most of you know, right, conventional wind turbines are upwind, and they're typically 3 blades. Now, when conventional wind turbines rotate, right, the blades are rotating in front of the tower. So the wind is coming in from the left, and for these upwind turbines, the wind is pushing back on the blades. And so as we're getting to larger and larger turbines and longer blades, in order to ensure that the blades don't get pushed back and strike the tower, we need to make sure that the blades remain stiff enough. And to keep them stiff enough, they end up being rather thick and very massive. And so then there's a lot of material costs that have to go into producing these blades. Now, if we turn downwind, so that the wind now is going to first go around the tower before it goes across the rotor plane. Then we can make the blades much more lightweight. The blades then will become much more flexible, and they'll actually naturally morph with the wind and kind of bend with the wind instead of trying to fight the wind. And that also means then that there are less stresses in the blade, which allows them to be lightweight and more flexible. Kind of all goes together. So this is akin to how palm trees go with the flow in tropical storms, right? They're very lightweight and the fronds morph downwind, and palm trees can survive hurricane conditions. This is in contrast to oak trees that, while huge and massive, they can get uprooted in severe storms, as shown here. So with this downwind concept then, when the winds are light, then the rotor will be pretty wide open and trying to maximize power capture. As wind speeds pick up, the blades will naturally morph downwind, reducing structural loads in the blade. And also by morphing downwind, that reduces the power capture area, naturally kind of regulating the power in these high wind conditions, because typically we don't want to be producing power that exceeds the rated power of the generator that's in the turbine. And so there are a lot of benefits here. Now, with this downwind concept, like the blades are lighter, that means that less material is needed to build them, and that makes them less costly. And if they're lighter, then they're also easier to transport and assemble. Now, as we are getting to extremely long blades, some of our collaborators on our overall team project, they're also exploring how blades can be manufactured in a segmented fashion. Most wind turbine blades these days are manufactured as one whole piece per blade. Being able to make the blades in multiple pieces will make them easier to transport. Now, wind turbines require large teams to design them. And usually it's a rather sequential, linear design process. The aerodynamicists design the shape of the blades. And then the structural experts then determine the layup of materials needed in the manufacturing process. Now, my group's research area is in the control systems area, and usually by the time that we're asked to design a controller for a wind turbine, all the other aspects have already been designed, and we're just asked to design the best controller that we can to make the turbine operate as efficiently as possible. That is, we want to generally try to have the wind turbine produce as much power as possible under the range of wind conditions expected. Now, I don't have time in the short talk to really get into the details of the controls that controller designs that we're developing. But one aspect, for instance, is that we measure the rotor speed, so that's how fast the rotor is spinning, and we decide how to pitch the blades. The blades can be rotated, and that changes the aerodynamics, and that can affect then how efficient the turbine is operating. So in this serial design process, there ends up being a lot of conservatism in the design. For instance, the structural designers might end up putting more material into the blades to try to make sure that the blades are strong enough, because they aren't sure how well our controllers will work ultimately. And so that means that ultimately the turbine might be more expensive than it needs to be. And so in our project, in part because we set some very, very aggressive milestones for ourselves, we ended up working more closely as a team. And by doing so, we found we could end up designing more optimized wind turbine designs. And we were able to recently show that by using what we call this co-design process, we're able to show that we could design a 13 megawatt wind turbine based on our downwind lightweight concepts, where we're trying to minimize the cost of energy. And we are able to show that the lightweight downwind concept can yield wind turbines that lead to a 25% reduction in the cost of wind energy compared to traditional three-bladed upwind designs. So that means that wind energy can be made even more economical than it already is. Now, in order to demonstrate new concepts, it's very important to be able to experimentally demonstrate it either in a wind tunnel setting or actually out in the field. And we were lucky enough to actually be able to do some field tests on a research turbine at NREL. And so what we did was we took one of our detailed 13 megawatt blade designs and we gravel aeroelastically scaled down to 20% scale. And so we ended up with blades that are approximately 21 meters long. And these blades were then manufactured and then ultimately mounted on one of these research turbine platforms at the NREL's National Wind Technology Center, just south of town. So we call this demonstrator the SUMER demonstrator, or SUMER-D. And this video here, should be playing now, it shows our constant blades on the test turbine. The turbine's actually in a parked situation here where it is not in operation, but when there are winds, it can still rotate. And hopefully you can see just how flexible these blades are. And so they're very lightweight, very flexible blades. And this next video shows the SUMER-D in operation. It's facing downwind in the opposite direction compared to the two traditional turbines. You can also see in the video. Now, our field test campaign ran from November 2019 to August 2020. And it was successful and super exciting. Our analysis of the data thus far shows that we do have the load alignment concept, and we also were able to show, of course, that the lightweight rotor was able to survive the rather extreme wind conditions that, as all of you know, does occur in this area. We are still continuing to analyze many aspects of the data, and we hope that this can further the technology in the future. So now I'd like to turn and talk about offshore wind energy. Now, why is there interest in offshore wind energy? So if we look at the wind map of the US, we see that we have a lot of winds, strong winds in the center of the country. And that's indeed where many of the land-based wind farms have been built in the US. Now, some of the best winds, though, are actually just off the coasts, off the east and west coasts, and as well as over the Great Lakes. Now, offshore winds tend to be stronger, more consistent, and a lot of the large population centers tend to be on the coast. So then it does make sense potentially to build offshore wind farms where we are providing power to nearby communities. Right. The current situation with a lot of wind in the center of the country is that oftentimes the power has to be transmitted much further to where it's needed. Now, I mentioned earlier that with land-based turbines, there are constraints on the maximum sizes due to the road and railway transportation constraints. Now, offshore, there are fewer constraints, and so turbines have continued to grow in size for offshore turbines. Sorry, it was advancing on me automatically. Now, I did want to point out, and I think it might have automatically played earlier. So there are currently two very small offshore wind farms in the US. One is this Block Island wind farm that's just off the coast of Rhode Island. And it is a 30 megawatt wind farm, which is very small. It's 5-6 megawatt turbines. And then, so that went into operation in 2017. And then just last year, there is a 12 megawatt demonstration project just off the coast of Virginia that consists of two 6 megawatt turbines. So these are shallow water, what are called fixed bottom wind farms. And we'll talk a little bit more about fixed bottom versus floating in a bit. All right, so now let's look at the growth of offshore wind power. So recall that the total wind power installed capacity, both land-based and offshore, is now more than 730 gigawatts worldwide. Now, installed offshore wind capacity has been growing at an average annual growth rate over the last decade at 28% globally. And that's twice as fast as the growth rate of wind power in general. So globally, the offshore growth is expected to continue at least at this annual growth rate, which means that there will be more than 110 gigawatts of offshore wind by 2025. So it's really tremendous growth. Now, at the end of 2020, global offshore wind was only about 4% of the total installed wind power capacity. Now, in terms of offshore wind, the UK is the #1 country. They're a small country with a lot of good coastline and have a lot of good resource. Okay. Germany is #2, and they've been growing tremendously fast over the last decade. This is average annual growth rate over the last decade. And then China is #3. Now, there's a lot of variability in these average annual growth rates over the last decade, and some of these are rather large, in part because there was so little offshore wind a decade ago. All right, now, as a percentage of total wind power capacity, you'll also see a lot of variation, right? And it depends on the country. As mentioned, UK has a lot of good coastline and good offshore wind resource, and so it has a lot of offshore wind. Now, China over recent years just has had a much larger growth rate compared to the other two countries, and projections forward and what's under construction, they're actually have, I believe, have already, I don't know why it's advancing by itself, they've already exceeded Germany, and I believe maybe this year they will actually surpass the UK, if not already. So the data that I'm presenting has been verified and published, and it's data through 2020. The 2021 data has not been verified and published yet. All right, so the UK, Germany, and China, the top three, they have about 75% of the offshore wind power capacity globally. And offshore wind right now is dominated by 6 countries, and there's really very little other offshore wind elsewhere. But there are a number of countries that are planning and already have many offshore wind farms in the pipeline. So countries that are expected to have more than 3 gigawatts of offshore wind power installed by 2025 include the US, South Korea, Taiwan, and Vietnam. All right, now, right now, more than 99% of commercial offshore wind worldwide, including both the small offshore wind farms in the US, uses what are called fixed bottom wind turbines, where the wind turbines are built all the way down to the ocean floor. So these are all shallow water wind turbines. Now, for water depths greater than about 60 meters, it doesn't make economical sense to build the wind turbines all the way down to the ocean floor. And here it's much more economical to use floating wind turbines, and several floating platform concepts are being investigated. Now, when you have a floating wind turbine, both the wind and waves can cause oscillations, and you need to make sure to try to keep the wind turbine upright and also try to produce efficient power. And so there are many challenging control issues. Now, about 80% of offshore wind resources worldwide are over water that is 60 meters or more deep. So floating offshore wind is expected ultimately to be quite a significant share of worldwide wind installations. And large-scale floating wind farms are expected to be deployed as soon as 2024. So locations where floating offshore wind farms are being considered include in the US, on the West Coast, where it's almost all deep water, and also in the North Atlantic, where there are large population centers and also a lack of shallow water sites. Floating offshore wind is also planned off the coast of Hawaii, as well as over the Great Lakes. Now, floating offshore wind farms are also being considered on the east coast of South America, initially more along this section, and then ultimately will expand further south. And floating wind is definitely being considered in Europe as well as in East Asia. Now, while there have been a number of smaller demonstration projects in operation for over maybe the last dozen years or so, there are only 2 commercial floating offshore wind farms that are larger than 20 megawatts. And by wind farm standards these days, these are very small wind farms. So one of these is called High Wind Scotland and is a 30 megawatt, sorry, I didn't want it to advance to the next slide. So one of these is called High Wind Scotland, and it's a 30 megawatt wind farm that began operating in 2017. And then WindFloat Atlantic is a 25 megawatt wind farm that is off the coast of Portugal and became operational in 2020. Now, the water depth at these two floating wind farm sites is about 100 meters. So some of the basic floating wind turbine platforms have been borrowed from platforms used in the oil and gas industry. So these end up being relatively sturdy, which is nice, but they end up being quite massive and hence expensive because of all the material needed to build them. Now let's take a closer look at the floating platforms or substructures at the two existing small floating offshore wind farms that I pointed out. Hywind Scotland has 6 megawatt turbines, 5 of those, that are on what are called spar substructures. And WindFloat Atlantic has 3 8.4 megawatt turbines on what are called semi-submersibles. Now you can't quite see what's underneath the water from these photographs. So let's look at an illustration of these platforms on the right. So somehow it's advancing by itself. So I wanted to make sure it doesn't go to the next slide. All right. Now, the floating wind turbine on a spar platform, the way that achieves stability is through a ballast with a deep draft. But one of the challenges of this type of floating platform is that most ports don't have deep enough water for such turbines to be assembled at port. And so then it's more complex to try to assemble the turbines closer to where they're actually going to be located. Whereas semi-submersibles, they achieve stability by distributing buoyancy widely at the waterplane. And the advantage of this design is that because of the shallow draft, these floating wind turbines can be assembled at port and then just towed out to their eventual sites with regular tugboats. And as such, this is one of the more popular floating platform designs right now. But the challenge with semi-submersibles is that because there's more of a floating platform above the water line, that leads to higher exposure to the waves. Now, to give a sense of size, the WindFloat Atlantic turbine here is an 8.4 megawatt turbine, and it has a rotor diameter of 164 meters. And so that's more than twice the length of the largest commercial passenger airplanes now. And each of these columns in the substructure, they are 30 meters tall, and they are 50 meters apart from one another. So these are really massive structures, and they have to be controlled well. Well, let me just briefly highlight one of the projects we're working on in the floating wind turbine area. So our project is called Ultra Flexible Smart Floating Offshore Wind Turbine, or US Float. And our focus is on the design of a novel platform that we call the spider float. So spider float refers to the platform, and US float refers to the entire turbine. So we're using a similar control co-design approach where we're specifically working very closely with the structural designers to better understand how we can try to reduce the mass and hence the material costs of the floating platform. And our role in the project is also to try to make sure the challenge, of course, as we reduce that mass in the platform, becomes harder to control. And we need to make sure that we can keep the turbine upright while still producing power efficiently. So hopefully you could see let me try to play it again, see this animation here. So the components of the spider float platform are modular, and they're designed for ease of manufacturing, transport, and installation. There are 3 legs, and there are cables that support the legs. And then there are clusters of buoyancy cans. The buoyancy cans are attached via universal joints, and this mitigates the transfer of loads. So rather than responding to the waves as a rigid unit, the spider float reduces the loads that are transferred to the tower and rotor. And so you can hopefully see that the buoyancy cans are in motion, really trying to isolate the turbine from the wave effects. However, as you can also see from the animation, the flexible spider float platform does have very complex dynamics. And so part of the goal of our project is to determine if we can overcome the challenging dynamics to reap the benefits of the spider float design, which is largely to try to reduce the mass in the platform in order to reduce the capital costs of the overall floating wind turbine. So in summary, we have found through several different projects now that this aerostructural control co-design process with an interdisciplinary team can be very productive in leading to better optimized wind turbine designs that reduce the cost of wind energy. Now, floating offshore wind installations are expected to grow rapidly for some time to come. The cost of floating offshore wind energy is expected to decrease to similar levels as for fixed bottom wind energy. So then it won't be a matter of only developing shallow water sites, but rather developing offshore sites that have good wind resource and choosing the fixed bottom or floating technology that is appropriate for that site. Now, given the global offshore wind resource available, floating offshore wind is expected to be a big part of the solution trying to mitigate and stop the climate change. There are many research groups and companies that are trying to minimize the cost of floating platform substructures, largely by trying to reduce the mass in these substructures. So a couple further general areas of future work that I'd like to point out are in the area of control of wind farms, which is quite an active research area right now for land-based and fixed bottom wind farms. So wind turbines interact with one another through their wakes. This is now a relatively famous photo of a shallow water fixed bottom wind farm just off the coast of Denmark. As the lead row of turbines extracts power from the wind, wakes are formed, and you can see that. Now, the wind speeds inside the wakes are lower and also more turbulent. So the turbines in the wakes here can't produce as much power due to those lower wind speeds, and they're also beaten up more because of the turbulence, and so they have higher structural loads, which could have maintenance and lifetime issues for the wind turbine. Now, it's now relatively well known that coordinating the control of the individual wind turbines on a wind farm can lead to overall greater power production across the wind farm. And wake effects are now also taken into account in optimizing placements and layouts of wind turbines on a wind farm. Now, there are a number of interesting open questions when considering floating wind turbines. For instance, a floating wind turbine, because it's moving, how does the wake behind floating wind turbines behave? Does the wake dissipate faster behind moving floating wind turbines? If so, that could lead to advantages for floating offshore wind farms, as they won't have as serious wake effects because the wakes potentially could dissipate before they reach that next turbine. Now, sorry, trying to find where I am. Okay, so also for floating wind farms, if the mooring lines are relatively slack, which often they are, would it be advantageous to control the turbines in such a way that we can shift them slightly translationally depending on, say, the wind direction? In this way, we can try to change the layout of the wind farm slightly depending on the wind direction, again, to try to mitigate the effects of the wakes in floating wind farms. So there are many open questions, especially related to floating offshore wind turbines and wind farms. And also, as I mentioned, as we're going to larger and larger, more extreme scale turbines, there remain many grand challenges. I was fortunate to be part of this group of researchers that put together an article that was published a little over 2 years ago now on what we view as the grand challenges in the science of wind energy, and much of what we said there still holds true now. Since that time, we've divided our group into several different groups where each group is focusing on a particular aspect, ranging from atmospheric sciences to grid integration issues. And the group that I'm in is focusing on the wind turbine, and we're writing more detailed follow-up articles on the challenges in each of these focus areas. And so those follow-on publications will hopefully appear over the next year. So stay tuned for that. So in closing, I do want to acknowledge the entire SUMR team. This is a photo of that team back in 2018 when our 20% scale concept blades were manufactured and ready for testing. This is one of those blades that were ultimately hoisted onto the turbine, and the video that I showed earlier was showing these flexible blades. So you can see that it's a relatively large team, and these large interdisciplinary teams are really great fun to work on, and we really do learn a lot from each other. I, of course, also want to acknowledge the US Float team as well. That project started after the pandemic hit, and we've actually never been all together as a team in person. But it's been still fun to work, even though through a lot of Zoom and Teams meetings. And more generally, I want to thank my research group for teaching me about many aspects in the control of wind energy systems. And of course, I want to thank our sponsors that have supported our research in the wind energy area over the last 5 years, in particular ARPA-E, the Advanced Research Projects Agency Energy, that has provided the primary funding for both of our SUMR and US Float projects. And last but not least, thank you all for listening.
Thank you so much, Professor Pao. That was wonderful, and we've received a lot of questions. And I encourage anyone that is listening, please go ahead and submit any questions that you have through that Q&A button at the bottom. We'll go ahead and close those now. So we have one question come in from Joanne. Joanne asks, can the ocean movement be harnessed as electrical energy?
Yes, that's a great question. So there are tidal energy systems as well as wave energy converters. And so these are very active research areas to try to harness the energy in the ocean. And as I mentioned, floating wind is expected to be a very large component of offshore wind. That together with tidal converters, wave energy converters, all of this is actually being called the blue economy. It's expected to be actually a major portion of the economy going forward.
Great. We had another question coming from Scott. Scott asks, while I was in the Middle East, I saw a vertical helix-shaped wind generator. What are your thoughts on this or other design alternatives to the conventional wind turbine designs?
Yeah, so that's a very good question. At the extreme scale, as we talked about today, the most developed designs are these what are called horizontal axis wind turbines, and primarily upwind turbines. So the downwind concept that we've been exploring over recent years, it's really much less developed. And what you mentioned is what's called a vertical axis turbine. So it's spinning along the vertical axis. Those, in terms of stability, structural stability, have only been proven at the much smaller scale. But I think there could be potential there, and that there are a number of groups actually exploring that. And so it's still yet to be seen whether those could be developed at the larger scale. One of the big advantages of those vertical axis turbines is they are omnidirectional in the sense that they don't necessarily prefer one wind direction. Whereas for the horizontal axis turbines, as I mentioned, they're facing into the wind. If the wind direction changes, they have to be yawed to face into the wind.
Great. We had a question from Dan. What is the potential for wind versus solar to contribute to our energy needs?
Yeah, so I think the cost of solar has really been dropping. I think it's now even lower than the cost of wind, and there's tremendous wind and solar potential worldwide. And I think many experts in the energy arena firmly believe, I'm one of them, that we can get to about 80% wind and solar penetration worldwide. And we hope, of course, the balance, the remaining 20% can come from other clean energy sources such as hydro, nuclear, geothermal, other clean energy sources, so that we can get to a fully clean grid.
Great. We had a question from Jeff. With Sumer, what are the effects of wind shadow as the blades behind the tower?
That's a very, very good question. Yes, so the reason upwind turbines have been prevalent is to try to avoid the tower shadow effect. So in the upwind case, right, as I pointed out, the wind comes through that rotor plane first and then goes around the tower. In the downwind case, the wind first goes around the tower and then the rotor. And so as that wind goes around the tower, it already becomes a little bit turbulent because it has to go around the tower. And so by the time it's going through the rotor, because of that turbulent behavior, then that's what the tower shadow effect is. We have found, and we have the field data that in terms of our demonstrator testing at the National Wind Technology Center, that the tower shadow effect is actually relatively small, especially because we have this light wind downwind concept where the blades are actually generally morphing further downwind. So they're actually further downwind from the tower. And because of that, some of that turbulent effect gets dissipated between the tower and when it actually hits the blade. So we have found it not to be a significant effect. There is a small effect, and we're still trying to analyze the data further and try to quantify that.
Great. I have a question from Donna. Could you please speak about the use of drones for inspecting wind turbines, especially offshore?
Yeah, so the use of drones is immensely helpful for inspection of wind turbines. And of course, it provides a way of inspecting turbines that can also then allow us to avoid having humans, going up into the turbines. It's quite dangerous in terms of some of these inspection requirements. And so drones are being used both for land-based wind farms and offshore wind farms. And a lot of this is still being developed in terms of really making the best use of these drones in inspecting turbines. But they can be used, and they can be used very effectively. And it is definitely at the forefront of most of the wind industry.
Great. Next question is from Nicholas. What kind of contingency plans are there for offshore wind farms during things like hurricanes and tsunamis?
Yeah, so yes. So wind turbines, when they're sited and when they're built, they have there are a lot of studies that go into trying to ensure that the turbines can survive the conditions of that site. Now, of course, you can have extreme events, maybe even more so than expected, that come through, such as tsunamis and hurricanes and typhoons and such. And so usually when these situations occur, what happens is actually you try to pitch the blades. So instead of having the blades be trying to capture as much power, you pitching them so that you're letting as much wind go by. So basically pitch all the blades, you put the brakes on, and essentially you're trying to brace through a storm, but you try to pitch the blades, get in a situation that you trying to let as much wind go by without impacting the structure as much. And so that is a concern, and that definitely in the research and industry community is a big area of evaluation and investigation. And so that is something we were concerned with our concept blades being deployed at the National Wind Technology Center. And so we were happy and a little bit relieved to see that our blades survived over quite some time on the turbine there, where the blades did experience well over 100 mile/hour winds. And so I think all those safety factors that we worked in terms of the manufacturing really did make everything work.
Great. We have a couple questions about the transfer of energy from these offshore turbines. So I'll pull this one from Lisa. How hard is it to arrange transmission lines from offshore wind farms?
Yeah, so that's actually, since it's very new, there's a lot of discussion of what's the best way to do that. A lot of times, and very much so far, even in the North Sea, in Europe, where they have a lot of shallow water offshore wind farms, it's largely been each wind farm figures out the transmission to land and to these substations and then onward. But as there's more and more offshore wind being developed, and especially if we look off our coast and what's in the pipeline, there's a lot coming. And so there's discussion that we should plan out these offshore grids in a more collective way, rather than having each wind farm figure out their solution. And so I think, I do hope that there will be kind of a collective, more optimized solution across all the offshore wind farms that are being planned.
Great. We had a couple questions come in too about potential environmental impacts. Is that something that your team is thinking about as well?
That is, so that's not our expertise area. So we don't maybe spend too much time on it, but it is something that we are concerned with. And so we definitely follow and try to make sure that we understand some of these effects. And if there's ways that we can help in our work to push that research forward, we definitely want to do that.
Great. This is a question I had as well. I know you showed a couple different designs of turbines that had either 2 blades or 3 blades. Can you speak to some of the advantages to each of those and when you might use one over the other?
Yeah, so the 3-bladed technology is very, very much better developed. We believe that there could be some advantages of the 2-bladed technology. But I think that there's still more work to be done to have that, fully assessed with enough certainty. And I think given the industry and how entrenched the 3-bladed designs are, all their processes are set up for 3-bladed designs. And so we really need to show a definite advantage of the 2-bladed designs before the industry is going to be willing to change their processes towards 2-bladed designs. I think there could be advantages, but it's hard to tell at this point.
Great. Question about kind of your design process. So before the full-size turbines go into development, will you be doing larger scale models in the 20% ones that you've previously done?
So say that again. I just want to make sure.
Yeah, before the full-size turbines go into development, will you be doing larger scale models than the 20% one that you've done?
Yeah, so that would be the goal. So we are actually working with an industry partner, and we hope that we'll, in the next phase of our project, which we hope we'll receive some funding for, will go to an even larger demonstrator. Probably not all the way to 13 megawatts, but maybe at the lower megawatt scale. That's usually the kind of the stages to before the full deployment at scale.
Great. Question here about the lifespan of the materials. So what is the estimated useful life of the tower, blades, and the turbine?
Yeah, so the wind turbines generally are designed to have a lifetime of 20 years. And oftentimes we see that wind farms get life extensions, so they go even to 25 years. Now, maintenance costs do go up as turbines age, and so you have what are called repowering efforts on wind farms. Well, they'll replace turbines with newer turbines, or sometimes replace a rotor, just the blades and the hub on a turbine sometime before they get to the end of the life. So it ends up being kind of an economic evaluation of when to replace turbines.
Great. I will wrap up. This will be our last question, and I'm sorry we couldn't get to all of our questions. We have a lot of you on our webinar today, so we thank you so much for your involvement. I'd seen some questions come in earlier. Folks seem to be curious about wind energy that's being harnessed in Colorado specifically. So this question says, can you talk about any advances in capturing wind energy in areas such as Colorado's foothills where velocity extremes exist?
Yeah, so that's a good question. I can see how people think that the Front Range area might be a good area for wind farms. So usually for wind farms, what we want and how wind turbines are designed, what we want is kind of persistent wind at approximately kind of this narrow range of speeds. And that unfortunately is actually not what we have on the Front Range, right? We have many calm days with almost no wind. And then of course we have many days with tremendously gusty, turbulent high winds. And so this is actually not a good area. You know, the Front Range is not a good area for wind turbines, which is why they're not sited here. So in Colorado, the wind farms tend to be in the eastern plains where they get more consistent winds. Now that NREL's National Wind Technology Center is sited where it is, in the foothills essentially, because they get these extreme wind conditions. So they're just east of El Dorado Canyon, and so they get these huge gusts that come through. And they're sited there primarily as a test site because they can test the extreme ranges of conditions that could occur. And so it allows a lot of wind turbine manufacturers will actually send some components or blades for testing at the wind site so that they want to see, you know, whether their components or blades can survive these extreme conditions. So it's a good testing area, but not for wind farms.
Great, perfect. Well, thank you so much, Professor Pao. This was an amazing presentation. I see that we've gotten a lot of really positive feedback in the chat already. So thank you so much.